Hello students! Today we're going to officially talk about the special properties of water. I know you've experienced them a little bit, but we're going to talk about exactly what's going on in there at a molecular level. So, polar covalent bonds. Water has two covalent bonds in it. It's got one between one hydrogen and oxygen, and the other between the other hydrogen and oxygen. And we also know that oxygen has 8 protons, while hydrogens only have 1. And because of that, the electrons are going to spend more time around this guy than they are around this guy, because this pull is way harder. So it's going to be slightly negative up here and slightly positive down here. So how is water formed? Like I said, 1 oxygen, 2 hydrogens. The oxygen has 6 valence electrons. How many does it want? Yeah, it wants 8. Where's it going to get those 8? Well, it's going to share them with hydrogen. Hydrogen wants 2 because it's just got that 1 inner shell. It is happy to just share one of oxygens, share another of oxygens, and now they're both going to get to use those. So hydrogen's happy, oxygen's happy because it's got that full valence shell. Hydrogen also has a full valence shell. Remember though, oxygen 8 pluses, while this is only 1 plus. Because of all that plus, all that positivity, the electrons want to be here more. Thusly, we have the difference in charge. This is more negative, this is more positive. And that's what makes it a polar molecule. It's like a magnet. Because of the location of the electrons, some molecules have an uneven distribution in the electrical charge. More positive here, more positive here, more negative here. Polar is just like the North and South Pole. One side is one way, one side is the other way. Water has its own poles, the positives and the negatives. There are also nonpolar molecules. These are molecules, these are compounds. Between carbon and hydrogen, they're going to share pretty equally. And because of that, it's distributed very nicely and evenly, and thusly it's nonpolar. And polar molecules don't mix with nonpolar molecules. Polar molecules like polar molecules, nonpolar molecules like nonpolar molecules. The treated side is nonpolar, hydrophobic, afraid of the water. Look at that cotton ball. Look at it. This side, treated. This side, not treated. Treated side, it's not getting wet. There's no water getting in there. And now untreated, very wet. Yeah, hydrophobic, right there. I thought you'd also like to see these guys get covered in mud. I know I'm not wrong. But this guy's not. The guy on the right is not covered in mud because he is covered in a hydrophobic substance. So, what is causing this to happen? The hydrogen bonds are what holds water molecules together. Each water molecule can form up to 4 hydrogen bonds, and that's where the slightly positives bind with the slightly negatives on another water. But they're weak compared to the bonds within the oxygen and the hydrogen. That's why they can be broken much more easily. That's why it's easy to go from ice to liquid instead of going from water to oxygen and hydrogen gas. And they form and reform often. So hydrogen bonds lead to interesting properties of water. It has very, very interesting properties such as cohesion, adhesion, surface tension, capillary action, solubility, high specific heat, and density. And let's talk about these guys. Cohesion. If you're cooperating with someone, you're working with someone that's like you, that has similar things, similar goals in mind. It's similar with water. Cohesion is the attraction of water to other water molecules, and it is responsible for surface tension because the water is not really pushing against things. It's just that the water likes other water so much that other things can't break through it. So water wants to stay together on top of that penny, and water wants to stay together enough that water striders, these little bugs, will actually float on top of that because water wants to hold on to other water so much. Cohesion. Adhesion is the attraction of water molecules to other substances, and it's adhesive to anything that it can form hydrogen bonds. Anything that is polar will form hydrogen bonds. That's why raindrops stick to cobwebs or blades of grass, and it's also responsible for capillary action. What is capillary action? Let me tell you about it. Capillary action is the liquid or the tendency for liquids to rise up in narrow tubes. As a result of this, their surface tension and adhesion are what's going to cause that. And surface tension is really just cohesion, where the water molecules want to stick together. Adhesion is the water sticking to the sides. This is why we have a meniscus in a graduated cylinder. But it's also important for life, because in life, adhesion is going to cause the water molecules to hold on to the sides of cellulose and xylem walls in trees, and hydrogen bonds hold the water together in xylem. That's what allows water to go from the root all the way up to the leaf. And the process that drives this is called transpiration. We'll learn about it later. As long as water is evaporating out of the leaf, it's going to keep being pulled up from the root, and adhesion and cohesion is going to hold that water together. Water is also the universal solvent, and that's because many substances on Earth are polar and will dissolve easily in water. And when they dissolve easily in water, the water is actually surrounding them. So if you put salt into water, it looks like a nice crystal shape when you add it in, but over time, that water is going to actually surround each of these, and that's why it becomes clear, because the water actually pulls it out of this crystal form so that so much water is surrounding it that you can actually see right through there. It also has interesting thermal properties. Thermal properties being, heating properties, energy properties. Water has a high specific heat. It can absorb or give off a lot of heat without changing temperature very much. It's a really good temperature stabilizer. It keeps things in a nice, normal level. It kind of buffers the temperature. Water also has a high heat of vaporization, meaning it takes a lot of heat before it'll evaporate. And that's great because if we're sweating, we want as much of the heat to go into that water before it gets evaporated. That's what cools animals down, and that helps with plant transpiration as well. Because you want a lot of heat going with, a lot of energy going with it when that energy is pulling it. And it also has a high heat capacity that makes sure that the oceans are stable. It moderates the Earth's climate. It prevents organisms from overheating. And that just basically means high heat capacity is that it takes a lot of heat to change water in terms of degrees. It's a lot of heat to get up to the 100 degrees Celsius, and a lot of heat to get down, needs to be removed to get down to the water freezing, which is very, very important for life. Ice is also less dense than water, and we've talked about that a little bit, but it's really important, and that prevents water from freezing from the bottom up. Again, if it froze on the bottom up, then the ice would stay down there forever, water would push up, and it'd be very, very, very difficult to ever have liquid water on Earth. Instead, ice forms on the surface first, freezing in the water releases heat to the water below, and that actually insulates the water, keeping it even warmer. And this also makes transitions from seasons less abrupt, which the less abrupt you can be, the easier it is for life to adapt to it. Here are some great videos, again, that you can click on from the slides that you'll be given as well. Let's talk a little bit about pH, though. pH of the solution is dependent on the relative number of hydrogen compared to hydroxide. If you notice, H and OH, that's two H's, one O. What is that? Yes, that's water. And that's why pure water has a neutral pH of 7, because it's got equal numbers of H pluses and OHs. And the pH scale, you've got, I'm sure you've heard of it before, acids, like battery acid, have lots and lots of hydrogens, whereas liquid drain cleaner and bleaches actually have a lot of hydroxide. And you know, drinking battery acid, drinking bleach is bad for you. Both ends of these pH, either low pH or very high pH, isn't good for you. What's healthy is a pure pH around here, maybe slightly lower than that in the blood, urine, and other things. So acids and bases, many solutes readily dissolve in water because of water's polarity. An organism, which might be as much as 70% water, holds a lot of things in there. Acids, they release the hydrogen ions when they're dissolved. The more hydrogen, the more acidic. Bases release hydroxide ions when they're dissolved. The more hydroxide, the more basic it is. And so buffers are important because we know one thing that all living things do is try to maintain homeostasis. And since we know the more H plus you have, the more acidic it is, the more OH minus it is, the more basic it is. We want these to stay nice and balanced in the body. That needs to be controlled. And so buffers are mixtures that react with acids or bases to keep the pH in a particular range. Cells have buffers in them that actually keep pH of the blood within the 6.5 to 7.5. Blood is actually a little lower at 6.4, but it has buffers in it as well to keep it there. And here are some more great, interesting videos.